Okay, so let's go ahead and work this this rotational kinematic problem. So we have this car that's slowing down, and we're asked some questions about the tire of the car. So first of all, we're asked to calculate the angular acceleration of the tire as the car slows down. Okay, now what's really important about this problem is that there is no slippage in the tire as the car slows down. Okay, so if there is no slippage then, what that means is that this little point on the tire is moving exactly the same speed as the little point on the road it's in contact with. Okay, now if the tire were slipping, that wouldn't be the case. But since it's in contact with the road the whole time, that means at whatever speed the road is moving past the car, that's how fast the tire, that little spot on the car's tire is turning. So if that's the case, then the tangential acceleration is equal to the acceleration of the car. Okay? So the acceleration tangentially of this little point on the tire is the same acceleration as the car. Therefore, the tangential acceleration is r times the angular acceleration. So angular acceleration then is the tangential or the acceleration of the car divided by the radius of the tire. Okay? And we're told that the acceleration of the car is -7 meters per second squared. The radius is 0.28 meters of the tire. And that gives you the number -25 radians per second squared. Okay? So there's our answer to part A. Now part B asks, how long does it take for the car to come to a stop? And so in part B then, what we know here is that the initial angular velocity is 95 radians per second. We know what the final angular velocity is. Okay, so what would that be? Well, the car comes to a stop, so the tire comes to a stop. So the final angular velocity of the tire is 0. And our angular acceleration is given in part A. And we want to know, what is the time? So if that's the question, you want to go to our little list of kinematic equations, and the best one to use is this one. The change in angular velocity is angular acceleration times the elapsed time. So the elapsed time is then the change in angular velocity divided by the angular acceleration. The change in angular velocity is the final minus initial angular velocity. So 0 minus 95 gives us -95 here. The angular acceleration is -25. So you do that calculation and you get the answer 3.8 seconds. Okay? Okay, so that's the time it takes to slow down. Now in part C, we want to know how many revolutions does the wheel go through in coming to a stop. And so all these parameters here are exactly the same for part C. And we have an additional piece of information, delta t. So if we go through our kinematic equations, we'll see that this one will tell us what angle the tire has gone through. It's omega initial delta t plus 1/2 angular acceleration delta t squared. Okay? So we plug these values in. Omega initial is 95. The elapsed time is 3.8 seconds. Plus 1/2 angular acceleration is -25. Delta t 3.8 seconds again. squared. Don't forget the squared there. So you do this calculation, you get the number 180.5. Now, that's in radians, okay? Because all these values were radians. This is radians per second squared. So that's radians. We're asked about revolutions. So to find the number of revolutions, well, there are 2 pi radians in 1 revolution. Okay? So you have to divide this by 2 pi. And when you divide that by 2 pi, you find the total angle we've gone through in revolutions is 28.7 revolutions. Okay? So there's our results for A, B, and C. Now I'm going to have to do some erasing here so we can do parts D and E. And we'll keep these answers because they may be useful for parts D and E. Okay, so for part A we found, let's fix this board here. For part A we found negative 25 radians per second squared. Part B we found 3.8 seconds. And then in part C we found 28.7 revolutions. Okay. Now in part D, my board is falling apart here. Okay. Now in part D, we're asked specifically, how far does the car travel before coming to a stop? Okay. Well, if the wheel has gone through 28.7 revolutions, so 28.7 revolutions, if we figure out the amount of distance that's covered, that will give us how far the car is gone. Okay? So in other words, if we wanted to know the total distance that the car has gone, we have to multiply the number of revolutions of the tire times the circumference of the tire. Okay, that'll tell us the total distance the car has traveled. And this works, this approach works, because the tire does not slip while we're traveling down the road. Okay, so that's how many revolutions we go through. And we have to multiply that by the circumference of the tire, which is 2 pi times the radius. The radius is 0.28 meters. So you multiply those, and you get 50.5 meters. Okay, so that's how far the car goes. Now in part E, we're asked to calculate the initial speed of the car. Well, remember that speed is related to velocity. Speed is related to angular velocity by this expression. So if we want to know what the initial speed is, we just have to calculate this for the initial angular velocity. So if r is 0.28, initial angular velocity was 95 radians per second, and you multiply those together and you get the number 26.6 meters per second. Okay? And this works, this equation here works only because of our no-slip condition. Okay? So imagine your tire is just spinning away at 95 radians per second, but it's slipping on the road. Your tire is just spinning. Okay? Your car would be traveling down the road at 0 meters per second then. So this expression works only if the tire is in contact with the road the whole time.